I'm really excited about this lesson, you guys. This is probably one of the most important lessons of the entire year. So we've talked about this notion of derivatives and integrals being opposites. We've called our results for integrals antiderivatives thus far. We've also talked about how an integral represents the area under a curve, the total change in a quantity, in this case position. But we've talked about how we have this problem where if the curve isn't a nice geometric shape, aka a rectangle or a trapezoid or something, we don't know how to find the area yet. So we've been kind of limited in the integrals that we can do, and we've used our calculator to find a lot of them. Well, here we're going to put it all together and take this notion of an integral being a total change and an integral being the opposite of a derivative, and we're going to come out the other side with a method of finding the area under fancier curves, right? So area under curves represented by polynomials is what we're going to be able to do by the end of the lesson. And the coolest thing about this is we're going to do this using all stuff now that you already know. So I'm starting with just an antiderivative, and I know that means add 1 to my exponent and then divide by it, right? And I'll throw in my constant, and then I'm just going to go ahead and simplify this and make it look nice. So I get negative 1/3 t to the third plus 3t squared plus t plus c. And now I'm asked, part B, what is one possible function s of t for Nadine's position? And this really gets back to this notion of the plus c. C stands for a constant, and that represents that I could put 5 there, I could put 1,000,000 there. It doesn't matter. When I take the derivative, I would still get my original function v, right? So here, I'm just going to make up a number. So all I'm asked is like a guess. What is one possible function for Nadine's position? So by the end of the lesson, we'll be able to answer this for real. But for now, we're just going to make one up. So negative 1/3 t to the third. And if you're feeling particularly brave, you can use a different example than I do. So I'm going to put in 22. I'm going to let c equal 22. And I just picked that number randomly. So you're going to get the same result here if you randomly pick a different number. I promise that you will. So if you're feeling particularly brave, we're going to use this function a little bit later. Pick a different number than I did for your notes. Okay, now we're asked to use our calculator to evaluate the integral and interpret it in the context of the problem. So I'm going to do that real quick. You guys did this way back when, right? So you know how to do this for sure. So I hit math, and then I'm going to hit the number 9, and the integral from 2 to 5 is what I want. And then I'm going to type in my function exactly as it appears, and it spits out 27. Okay, that's 27, and my units was meters. And my interpretation is going to be the total change in Nadine's position from t equals 2 to t equals 5 seconds was 27 meters. And we could also say this is the total displacement, right? Which means the same thing as change in position. Okay, so now notice for part D, we're asked to also find a total change in position, right? So that S stands for position. We want S of 5 minus S of 2. So this means the same thing as our integral, but we're asked to use this function that we made up, right? And I made up 22, right? I used 22 as my constant. You maybe made up something different. Use your function here for part D. And the way that I'm going to do this is by using the evaluation function on my calculator. So I'm going to do second calc value, and we'll plug in 5. We get 181 over 3, which is 60.3. Repeating, and then S of 2, we get 100 over 3, which is 33.3 repeating. So these are the positions at these times. And notice the difference here. S of 5, if I subtract these two values, minus S of 2 is going to be 27, right? So notice, this is cool, right? We got the same value, 27, 27. So the same value in our change of position. Then when we use our made up, remember we made this number up. You maybe use a different one, and you can change that number in your calculator right now and see. We get the same result. It doesn't matter that we made it up. That's mysterious, right? How can that be? Maybe we'll explore that a little bit later, but for now we're going to make this note that our integral from 2 to 5 of v of t, well, that was equal to s of 5 minus s of 2. Right? So we get the exact same result. Those are equivalent. This is profound, right? Because what this means is to evaluate this integral, I can just take any antiderivative and plug in my two values and subtract the difference. And then these last two, we already know how to do e. It's going to help us get to f, right? So f asks us for the actual position function. Well, what we would do here, we've done this before, right? Is we would take 12 plus 27 would give me 39 meters at t equals 5. So we want the starting position plus the total change, right? The way I'd write this in my integral notation is I would say, well, s of 5 is equal to s of 2 plus my total change, right? So these things are all related. They're all just restatements of the same things. And then finally, we're asked to find her actual position function. So remember, we had a candidate we're going to find the exact one now. And we're going to use this piece of information that was given in part E along with our answer to part A. So I'm going to rewrite what we had for our antiderivative. So s of t, we said was this, right? And then remember, c is our constant. We kind of made that up. We don't know what that is yet, but now we have enough information to find it. So I'm given that s of 2 is 12. Well, that means when I plug in 2 to this, I should get 12, right? So I can just make myself an equation. And I am not going to solve this for you because this is an equation that you know how to solve. But that number that it spits out is c equals 2/3. So that gives me my s of t, right? So I get negative t to the third over 3 plus 3t squared plus t plus 2/3. Okay, so notice now we've developed two methods here. We can find a function given its derivative and a point on the curve, or we can find the area under a curve now by hand, and they're both related to what we already know about integration. In fact, that first result, and we did this in example D, is so important that it's called the fundamental theorem of calculus. And what this says is that to find a definite integral from a to b of any function, well, that's equal to capital F of b minus capital F of a. And the key here that makes this a little trickier to understand is that capital F is meant to represent any antiderivative of f, right? So to do a definite integral, find an antiderivative and then plug in the bounds and subtract them is what this is saying. And then my indefinite integral is what we did in example F. And that one I think was a little bit easier, right? We just found an antiderivative and we used a point to solve for c. Okay? So now you're equipped to answer tons of questions about integrals that you weren't before.